You are sitting inside a heated house right now, wrapped in blankets, wearing warm socks, with a thermostat on the wall set to exactly the temperature you want. And you're probably still a little cold. Meanwhile, 600 years ago, a Native American elder was sleeping on the open prairie in what looked like a tent made of animal hides and wooden poles. Outside, the temperature had dropped to -30 degrees Celsius. Wind was screaming across the flatlands hard enough to knock a grown man off his feet. Snow was piling against everything in its path. And that elder woke up the next morning warm, rested, and completely fine. No thermostat. No electric blanket. No insulated walls. No backup heating system. No emergency services to call if something went wrong. Just hides, fire, and knowledge so sophisticated that modern engineers who have studied tipi design have been genuinely shocked by what they found. And here's what makes this truly remarkable. Those winters weren't rare disasters. They came every single year, brutal and predictable, rolling across the Great Plains with temperatures that would kill an unprepared modern person within hours. Native American families didn't just survive those winters. They slept through them comfortably, raised children through them, kept elders alive through them, generation after generation for centuries. Before we reveal exactly how they did it, drop a comment with where you're watching from. And if stories of ancient survival wisdom fascinate you, hit that subscribe button because what you're about to learn will make you question everything you think you know about primitive versus advanced and will completely change how you see one of history's most sophisticated survival systems. Most people who look at a teepee today see a simple cone-shaped tent. They see animal hides draped over wooden poles and think, that's it? That's what kept entire families alive through winters that should have killed them? But that assumption reveals exactly how little most people understand about what a teepee actually was. Because a teepee wasn't a tent. It was a precision-engineered thermal system disguised as a tent, and every single element of its design served a specific survival function that took generations of observation and refinement to perfect. But before the teepee could do its job, before a single hide was raised or a fire was lit, Native American families had to make a decision that could mean the difference between survival and death. And most people never think about this decision at all. Where to put it? Location wasn't a preference or a convenience. It was the first and most critical survival calculation, and getting it wrong meant the entire system failed no matter how perfect everything else was. Native families read the landscape the way modern engineers read blueprints, identifying every factor that would affect temperature, wind exposure, and fuel availability before a single pole was planted in the ground. The first rule was absolute: never on open ground. The wind that swept across the Great Plains in winter wasn't discomfort. It was a killing force. Wind strips heat from any surface it contacts with brutal efficiency. A teepee on exposed flat ground facing open wind would lose heat faster than any fire could replace it, creating a situation where the family inside was essentially in a slightly warmer version of the outside air with no protection from wind chill. Smart families positioned their camps behind natural windbreaks. Tree lines, rock faces, ridge lines, any natural feature that could interrupt wind flow before it reached the camp. These windbreaks could increase the effective temperature inside the teepee by several degrees simply by eliminating wind chill from the thermal equation. And in temperatures that were already life-threatening, several degrees wasn't comfort. It was survival margin. Rock faces and cliff walls offered an additional benefit that reveals sophisticated understanding of thermal physics. Stone absorbs solar radiation throughout the day, storing heat in its mass. After dark, when temperatures plunged, those rock faces radiated stored warmth back outward. Families who positioned their camps near appropriate rock formations were essentially using the geology itself as a passive heating supplement. Valley positions offered wind protection but required careful judgment. A valley that blocked wind was valuable. But valleys also collect cold air through gravity. Cold air is denser than warm air, so it flows downward and pools in low areas, creating frost pockets where temperatures drop significantly lower than surrounding terrain. A family that chose a valley for wind protection without understanding cold air pooling could find themselves sleeping in a location colder than the open prairie they were trying to avoid. The fuel calculation was equally non-negotiable. A camp with perfect wind protection and ideal thermal positioning was worthless if the family ran out of firewood in the middle of a storm. Survival real estate required accessible deadfall within reasonable distance, wood that could be gathered quickly even in deteriorating weather. Running out of fuel during a blizzard wasn't an inconvenience. It was a death sentence that gave you a few hours before hypothermia made the decision for you. This location knowledge wasn't instinct. It was accumulated wisdom, passed from grandparents to parents to children over generations of trial and error where errors meant dead family members. By the time a young adult was making these decisions independently, they had years of guided observation behind them. They'd watched experienced elders read the landscape and make these calculations. They understood not just what to look for but why each factor mattered. Once the right location was chosen, the tipi itself became the second layer of the survival system. And here's where modern people consistently underestimate what they're looking at. The tipi's cone shape wasn't aesthetic or traditional in some arbitrary sense. It was aerodynamic. Wind flowing over a cone-shaped structure follows the curves and passes over it rather than slamming into a flat surface. The same wind that would batter and destabilize a square or rectangular structure flowed around the tipi, reducing heat-stripping wind contact with the hide surface. The hides themselves were the product of extensive processing. Raw buffalo hide is heavy, stiff, and relatively poor as insulation. Properly processed hide, scraped to consistent thickness, smoked to waterproof the fibers, and worked repeatedly until supple, became a different material entirely. The smoking process was particularly critical. It drove oils into the hide fibers that prevented them from stiffening when wet and created a water-resistant barrier that prevented moisture from penetrating and eliminating the material's insulation value. Multiple hides were sewn together to create the tipi cover, and the seams were positioned and sealed specifically to prevent wind infiltration at the joints. A poorly sewn tipi cover with gaps at seams was like a wall with holes in it, all the wind protection of the cone shape undermined by cold air infiltrating through the stitching. At the base, the tipi cover was weighted down or staked to the ground to prevent wind from lifting the edges and allowing cold air to rush underneath. This bottom seal was critical because cold air is denser and flows at ground level. An unsealed base meant cold air infiltrating directly into the sleeping area where it would pool and create life-threatening conditions. But the most ingenious element of tipi design was the internal liner. Most people who study tipis casually don't even know the liner existed. It was a second layer of hide positioned inside the tipi, attached to the poles and hanging from a height of roughly 2 meters, creating an air gap between the liner and the outer cover. This air gap was the thermal engine of the entire system. Cold outside air that penetrated through the outer hide cover or seeped under the base would contact the liner rather than entering the living space. Meanwhile, warm air from the fire inside rose through the air gap between liner and outer cover, creating a chimney effect that drew cold air from the bottom of the gap upward and out. This convection current served two simultaneous purposes. It prevented cold air from entering the living space by maintaining positive pressure inside the liner. And it drew smoke upward toward the vent at the top, solving the ventilation problem that would otherwise fill the enclosed space with toxic combustion gases. The vent at the top of the tipi, the smoke flaps, were adjustable. 2 flaps with poles attached could be repositioned from inside to change the vent opening's direction relative to the wind. When wind came from the east, the flaps were adjusted to prevent wind from blowing back down into the tipi and to maximize the chimney draft that pulled smoke upward. This wasn't a fixed feature. It was a dynamic control system requiring constant adjustment as wind conditions changed. Someone had to monitor this system throughout the night. The fire tender wasn't just maintaining the fire. They were operating the entire thermal system, adjusting the smoke flaps, managing fire intensity to balance heat output against smoke production, monitoring the liner for drafts, and ensuring the carefully engineered convection pattern that made the whole system function continued working through the night. The fire itself was small by the standards of what modern people imagine when they think of keeping warm with fire. A roaring bonfire would have been catastrophic inside a tipi, producing smoke faster than the vent system could evacuate it and creating fire risk in the hide structure. The fire was deliberately small, carefully maintained, positioned in a shallow pit in the center of the teepee. The pit depth mattered. A shallow pit below the surrounding floor level created a specific airflow pattern where cold fresh air entering at the base of the liner flowed along the floor toward the fire before being heated and rising. This drew fresh oxygen to the fire efficiently while keeping the coldest air away from the sleeping people positioned around the fire's perimeter. The stone lining around the fire pit served multiple functions. The stones prevented the fire from spreading, which was non-negotiable in a structure made of hides. But the stones also absorbed heat during the fire's burning and released it afterward, extending the effective warming period beyond when active burning was occurring. Hot stones played an even more direct role in the sleeping system. Smooth river rocks with no internal moisture that would cause cracking were heated in the fire, then wrapped in hides and placed under the bedding or near the bodies of the most vulnerable sleepers. A properly heated stone could maintain warmth for 6 to 8 hours, providing a personal heat source that didn't require the fire to burn at maximum intensity throughout the night. The ground itself was the third layer of defense against cold, and it required as much deliberate engineering as anything above floor level. Cold penetrates upward from frozen earth through conduction with the same efficiency that cold air steals heat through convection. Sleeping directly on frozen ground was equivalent to sleeping on a massive block of ice that would drain body heat through the night regardless of how warm the air above was. The floor system began with woven willow mats that created a physical barrier between bodies and the earth while also trapping air in the woven structure. Air pockets in the mat prevented direct conduction from ground to sleeper. On top of this went thick layers of dry grass, packed deliberately to a depth that provided meaningful insulation while remaining breathable enough to prevent moisture buildup. Then came the hides. Buffalo, elk, and deer hides were placed fur side up, leather side down. The fur side trapped warm air from bodies in thousands of tiny air pockets between the individual hairs. The leather side created a wind barrier that prevented drafts from penetrating upward through the insulation layers from below. This multi-layer floor system, willow mats to dry grass to hides, created a thermal barrier that could maintain sleeping surface temperatures dramatically higher than the frozen earth below. People were essentially sleeping on a constructed insulation assembly that separated their bodies from the killing cold of the ground. The teepee design, the location strategy, the floor system, all of it was brilliant. But none of it was enough on the coldest nights without the most powerful heat source Native American families had access to. It wasn't the fire. It wasn't the stones. It was each other. Native families sleeping in teepees during brutal winter nights didn't spread out across the floor the way modern people sleep in separate beds in separate rooms. They packed together deliberately, bodies pressed against bodies, arranged in specific configurations that maximized shared thermal benefit for every member of the group. The arrangement wasn't random. It was calculated with the same precision as every other element of the survival system. The most vulnerable members, the very young children and the elderly, were positioned closest to the center where heat from the fire was most evenly distributed. Adults and older children formed a protective ring around them, their bodies acting as both heat sources and wind barriers. The physics behind this arrangement were perfectly understood through generations of observation, even without formal scientific vocabulary. One human body generates roughly 80 to 100 watts of heat continuously. Two bodies pressed together don't lose heat twice as fast as one, because shared surface area means less skin exposed to cold air. The more bodies packed together in a shared thermal envelope, the more efficient the whole system became. A family of 8 sleeping in tight formation under shared hides created a collective thermal mass that maintained warmth far more effectively than 8 individuals sleeping separately ever could. The combined body heat raised the temperature inside the shared bedding to levels that individual bodies alone couldn't achieve. The hides covering this sleeping cluster were layered with the same deliberate system as the floor beneath them. The innermost layer was soft processed hide against skin, chosen specifically because soft hide wicks moisture away from the body surface. Moisture management was critical. Damp skin loses heat dramatically faster than dry skin because water conducts thermal energy away from the body much more efficiently than air. The middle layers were thick fur hides, buffalo being the most prized for their exceptional insulating properties. Buffalo fur has a unique structure where individual hairs are dense and crimped, creating maximum air trapping per unit of thickness. The air pockets between thousands of individual hairs were the actual insulation, each tiny pocket preventing heat transfer through the layer. The outermost hide layer was the heaviest and densest, chosen for wind resistance rather than softness. This outer layer prevented drafts from penetrating through the bedding pile and displacing the warm air trapped in the layers beneath. The weight also mattered. Heavier outer hides pressed down against the layers beneath, conforming to body shapes and eliminating gaps where cold air could infiltrate. Tucking was as important as layering. Hands were pulled inside the bedding and pressed against the body or tucked into armpits where blood vessels run close to the surface and body heat concentrates. Feet were pulled up toward the body's core rather than extended outward where they would lose heat rapidly at the bedding's edges. Children were completely enclosed in their wrappings, only faces exposed, with every extremity folded inward and secured. The attention to extremities reveals understanding of how cold actually kills. The body's survival response to cold is to restrict blood flow to the extremities, reducing heat loss from the surface while maintaining core temperature. Fingers, toes, ears, and the nose lose circulation first, making them vulnerable to frostbite even when the body's core is maintaining adequate temperature. Protecting extremities wasn't about comfort. It was about preventing tissue damage that would impair function and potentially become life-threatening through infection. Moccasins worn to sleep were often stuffed with dry grass that provided additional insulation around feet. Fur mittens kept hands protected. Small children had their feet wrapped separately in pieces of fur before being enclosed in the larger sleeping bundle. Every extremity received specific attention because experienced adults had seen what frostbite did and understood prevention was the only option. But there was a crucial rule that governed all of this body heat management, one that seems completely counterintuitive until you understand the logic. Don't sweat. Going to bed overheated from physical activity meant damp clothing and damp skin. And damp insulation, whether that was clothing, hides, or the grass in moccasins, lost most of its effectiveness immediately. A person who crawled into their sleeping bundle while sweating from exertion would spend the night in insulation that had been compromised by moisture, losing heat at rates that the body couldn't compensate for. So the evening routine before sleep involved deliberate thermal management. Enough activity to ensure the body was warm and circulation was strong, but stopping well before sweating began. This transition from evening activity to sleep preparation was understood as a critical step, not an arbitrary bedtime routine. When temperatures dropped to their most dangerous levels, when the fire was burning low and even the collective body heat of the sleeping family wasn't enough, Native American families employed a method that shocks modern people when they first hear it. They rubbed animal fat directly onto exposed skin. Buffalo tallow was the primary material. Thick, dense, and slow to melt at body temperature, it created a physical barrier on the skin surface that trapped a thin layer of warm air directly against the body while blocking wind from contacting skin directly. This wasn't moisturizer or a cosmetic application. It was thermal armor applied to the body's largest organ. The fat layer worked through two mechanisms. First, it physically blocked wind from reaching skin, eliminating wind chill effect at the body surface. Wind chill kills by stripping the thin layer of warm air that the body naturally maintains against the skin. A fat barrier prevented that stripping, effectively eliminating wind chill from the thermal equation regardless of what the wind was doing. Second, fat has low thermal conductivity compared to unprotected skin. Heat transfer from the body surface to the cold air outside slowed when fat was present as an intermediary layer. The body lost heat more slowly, reducing the metabolic demand required to maintain core temperature. Campfire ash mixed with the fat created a paste that added another dimension to the protection. The fine carbon particles in ash absorbed radiant heat from the fire and held it, creating a surface on the skin that actively retained warmth rather than passively blocking cold. This mixture was applied specifically to the most vulnerable areas where blood vessels ran close to the surface: wrists, ankles, temples, the sides of the neck. These pulse points were where blood was closest to the surface and most vulnerable to rapid cooling. The ashen fat paste was also applied to cheeks, foreheads, and the areas around the eyes on the coldest nights, the exact areas most exposed to cold air during sleep when faces remained uncovered for breathing. What looked to outside observers like face paint was actually targeted cold protection applied to the spots most vulnerable to frostbite. For children, this application was done by adults before sleep, ensuring that the smallest and most vulnerable family members had full protection even when they couldn't apply it themselves. An elder carefully smearing fat across a young child's face while wind hammered the tipi walls outside wasn't performing a ritual. They were doing the same thing a modern parent does when applying sunscreen before sending a child outside, applying a protective barrier against environmental damage, just with very different stakes. The protection of children and elders received dedicated attention that went beyond fat application and extra bedding layers. The sleeping position of these most vulnerable members was monitored throughout the night by adults who took turns staying partially awake. Adults rotated watch duties, not just for the fire but for the vulnerable sleepers. Someone was always checking that the children's coverings hadn't shifted, that the heated stones near the elders hadn't cooled below effectiveness, that no one had rolled into a position where part of their body was exposed to cold air. This nighttime monitoring was exhausting for adults who needed their own sleep, but it was understood as non-negotiable. Children were often wrapped in 5 or 6 layers of hide, while adults made do with 3 or 4. Elders received doubled bedding because experience had taught that older bodies generated less metabolic heat and lost it more quickly. The allocation of the warmest sleeping positions and the most generous bedding to those least able to maintain their own temperature reflected understanding of differential vulnerability that was accurate and effectively applied. Heated stones placed near sleeping children and elders were monitored carefully. A stone that had cooled completely provided no warmth but could actually draw heat from the body if it had dropped below body temperature. Adults checked the stones periodically, replacing cooled ones with freshly heated stones from the fire, maintaining the supplemental heat source through the critical overnight hours. What this required of the adults maintaining the system was significant personal sacrifice. Sleeping poorly to monitor children. Giving up the warmest sleeping positions to elders. Waking repeatedly to feed the fire and replace stones. Taking the outermost sleeping position in the family cluster where cold was most intense. These weren't passive comforts enjoyed by the family. They were active duties performed by capable adults who understood that the survival of the most vulnerable depended on their vigilance. The tipi camp itself was organized beyond just the individual shelter to create community-level thermal protection. Multiple tipis in a camp were positioned in deliberate arrangements that provided mutual wind protection. The outer tipis shielded the inner ones. Camps weren't scattered randomly across a site, but clustered with the gaps between structures minimized to reduce wind channels between them. This community organization meant a lone family in a single isolated tipi faced greater thermal challenges than a family in a clustered camp where surrounding structures provided additional wind protection. Survival was partly individual capability and partly community architecture. The dogs that lived in and around tipi camps served multiple functions in the winter survival system. As guards against predators, they provided security that allowed the family to sleep without posting constant watches, conserving human energy for thermal management. But dogs also contributed directly to warmth. Large dogs sleeping inside the tipi or pressed against the outer cover added metabolic heat to the thermal equation. Children sleeping with dogs was practical thermal management as much as companionship. The knowledge system that maintained all of these practices was transmitted through direct participation from the earliest age. Children didn't learn about tipi survival from lectures or demonstrations. They experienced it, participated in it, and gradually took on more responsibility for it as they grew. A child who had spent years watching adults position the smoke flaps, select heated stones, apply fat to skin, and arranged the sleeping cluster knew these practices as lived knowledge rather than learned theory. By the time a young person was making these decisions for their own family, they had years of guided practical experience. They'd watched what happened when smoke flap management was poor and the teepee filled with smoke. They'd felt the difference between sleeping on properly layered bedding and inadequate bedding. They'd seen how quickly a fire burned through different types of wood and what happened to the family's warmth when the wood supply ran short. This experiential knowledge base was more reliable than any written instruction because it included the judgment developed through direct observation of consequences. Knowing that smoke flaps needed adjustment wasn't enough. Knowing exactly how much adjustment, in which direction, under which wind conditions, was the knowledge that actually kept people alive. The entire teepee survival system functioned because every element reinforced every other element. The location reduced wind exposure so the teepee structure didn't have to combat maximum wind force. The teepee structure and liner created the thermal envelope that made the fire's modest heat sufficient. The fire heated the stones that provided supplemental warmth to the bedding. The layered floor system prevented ground cold from undermining the air temperature the fire maintained. The layered bedding and body heat clustering maintained personal thermal comfort through the night even as fire intensity dropped. The fat and ash application provided individual protection for the most exposed skin. The adult watch system ensured that nothing in this carefully maintained system failed without immediate response. None of these elements worked in isolation. The best teepee in a poor location failed. Perfect location with inadequate bedding failed. Good bedding with insufficient fire management failed. The system only worked when every element functioned correctly together, which is why the knowledge transmission across generations was so critical. Losing any piece of the system meant losing the whole system's effectiveness. When researchers and engineers have studied teepee design with modern thermal analysis tools, they've consistently found that the design achieves remarkable efficiency relative to its material simplicity. The convection system created by the liner and smoke flaps, the aerodynamic shape, the multi-layer construction, these features reflect solutions to thermal engineering problems that weren't solved in Western architecture until centuries later. Native American families sleeping comfortably in temperatures of -30 degrees Celsius weren't doing something mystical or superhuman. They were operating a sophisticated thermal system that addressed every mechanism by which cold kills: wind chill, conductive heat loss through the ground, convective heat loss into air, radiant heat loss from the body surface, with specific countermeasures developed through generations of observation, refinement, and knowledge transmission. They never froze to death sleeping in teepees not because they were tougher than modern people or genetically different. They never froze because they understood cold completely and had developed a complete system for defeating it. Every element of that system, from choosing where to put the teepee to the fat on a sleeping child's cheeks, was knowledge that worked because it was accurate, because it addressed real physical mechanisms, and because it had been tested by consequences severe enough to eliminate anything that didn't actually work. That's the real lesson of how Native Americans never froze to death sleeping in teepees. Not that they were braver or harder than modern people, but that they understood their environment with a depth and precision that turned a cone of hides and poles into one of the most effective cold-weather survival systems ever developed by human beings working with nothing but natural materials and the accumulated wisdom of generations who had faced the same killing cold and figured out exactly how to survive it.